Welcome back to the American Urological Association Biostatistics Chat. I'm Dr. Rena Malik, urologist at the Long Beach VA Medical Center. I'm joined here with Melissa Ossel, who is a biostatistician at Memorial Sloan Kettering for over 10 years. She's also been an editor at the European Urology Journal since 2016 and has been working with the Journal of Urology since 2018 and is now one of our chief biostatisticians for the last couple of years. Today, we're talking about difference between clinical significance and statistical significance. So, Melissa, can you tell us exactly what are some issues that you see most often when you're comparing clinical versus statistical significance?
Thank you for letting me speak on this topic, because one of the most common errors that I see as a statistical reviewer is that the authors are not truly appreciating the difference between clinical and statistical significance. And not fully appreciating both of these aspects can often lead the researcher to the wrong conclusion.
Let's talk about what exactly is statistical inference.
Sure. So statistical inference comprises two aspects. So the first is inference, which is, I think, what most people ascribe to this. It's the process of hypothesis testing or generating that p-value. And it asks, is something there? But there's a second critical component that researchers often look, which is estimation, which asks, how big is that something? And that's the process by which we generate effect size estimates and confidence intervals.
Let's get back to inference. What exactly is a p-value? I mean, we all see them, we use them, but how do you define one?
So one of the most ubiquitous pitfalls that we see in reporting is misunderstanding around that p-value. So getting back to basics, I want to throw up a multiple choice question here. So what is a p-value? Is it A, the probability of making an error by rejecting a true null hypothesis? B, the probability that the data would be at least as extreme as those observed if the null hypothesis were true? C, the probability that the null hypothesis is true, or conversely, that the alternative hypothesis is false? Or D, the probability that the data were produced by random chance alone? A is actually what's known as a type 1 error, meaning you're incorrectly rejecting a null hypothesis. Our correct interpretation of a p-value is answer B. P-values are calculated based on the assumption that the null hypothesis is true for the population, and it is the probability of observing a sample as extreme or more than what our data show. Consequently, p-values can't tell you the probability that the null hypothesis is true or false, because the calculation assumes that the null hypothesis is true. So C is incorrect. And D, researchers often wish to turn a p-value into a statement about the truth or probability of a null hypothesis, or the probability that random chance alone produced that observed data, but the p-value is neither.
So I think the big take home is that your p-value, your inference is assuming that your null hypothesis is true. And so how do you then interpret a p-value?
You can think of a p-value or hypothesis testing in general kind of analogous to a court case. So in a court case, the verdict is either you're guilty or you're not guilty. There's no such thing as an innocent verdict. And the same goes for hypothesis testing. We either reject or we do not reject the null hypothesis, but we never accept a null hypothesis. And for more discussion about this, you can see our guideline 3.1.
Now, you said there was two components, right? And you said there was inference and estimation. So when does estimation come into play?
So estimation will always come into play. And I have a good example to illustrate why. So if we pull up table 1, we see a table that illustrates differences in age and family history by two different treatments. So we see here that both p-values are statistically significant. But p-values can be extremely small if you have lots of statistical power, which happens when you have either a large effect size or you have a very large sample. In this case, we have 5,000 patients in each treatment arm. And so differences comparing a median of 49.9 years of age versus 51.1 years of age is statistically significant, albeit probably not clinically significant. So even in the case where your p-value is less than 0.5, it is essential to provide those estimates of effect sizes. And you can see guideline 4.4 and 4.5 in our guidelines for more discussion about that. that point.
What do you exactly do with a negative study, meaning the p-value is greater than 0.05? How do we interpret that and use that?
So in that case, we don't have enough power to reject the null hypothesis. And again, we must not accept the null hypothesis. The absence of evidence is not evidence of an absence in a statistical sense. So I have another example here. If we throw up table 2, say Michael Jordan and I each took 10 free throws, and I miraculously made 1, and Michael Jordan made 5 free throws. If we took our Fisher's exact test p-value, that p-value is greater than 0.05. However, I don't think anyone would consider Michael Jordan and my free throw ability to be comparable. And that's going to be illustrated by the risk difference here. So when we look at the risk difference and 95% confidence interval, we see that Michael Jordan's free throw percentage is up to a 76% higher free throw percentage than my own based on this one small sample. The NBA or WNBA scouts still have not come knocking on my door. A large p-value simply flags that the data are not unusual if all the assumptions were satisfied to test that result. Again, it is critical to provide clinically interpretable estimates of our effect size along with a corresponding confidence interval. And then we can look at that confidence interval and ascertain whether that includes effect sizes of clinical importance.
Let's take it back. What exactly is a confidence interval and how do we interpret it?
This is a great question. A confidence interval gives us a measure of how precise our estimation is, and it represents effect sizes most compatible with our data. So in a similar sense, p-values can be very small, but they are never 0. And similarly, confidence intervals exclude no value, no matter how far outside the interval that value lies. Let me give you the exact definition of a confidence interval. A 95% confidence interval means that if we were to take a large number of different samples and compute a 95% confidence interval for each sample, then on average, 95% of those confidence intervals will contain the true effect size. So the 95% of a confidence level refers only to how often those 95% confidence intervals computed from very many samples will contain the true effect size if all the assumptions used to make that confidence intervals are correct. So in order to make our conclusions, we need to look at whether or not our 95% confidence intervals include clinically relevant effect sizes.
Do you have an example that you could share with us that a little bit to help people really understand that?
In our table 3, that our confidence interval does not include more than a 3.9% increase associated with being treated with treatment A as compared to treatment B. So we might say, although the association was statistically significant, it was not clinically significant because we don't really care about an increase in nausea of, such a small percentage increase. However, if the outcome was, say, death within 7 days, a 3.9% increase might be very much clinically significant as well as statistically significant.
That's very helpful. So can you give us some language as to how we can write this in words when we're interpreting both statistical significance as well as our confidence interval, and how we can kind of convey those findings better?
Yeah, absolutely. I have one more table with a couple of illustrative scenarios. So depending on whether you have a statistically significant result or your confidence interval includes clinically significant differences. So in the case where we have a statistically significant association and our confidence interval includes clinically significant differences, we might say something like, we found a statistically and clinically meaningful association. In the case where our confidence interval includes something clinically meaningful, but we didn't have statistically sufficient evidence, we might say something like, we did not have sufficient evidence of a statistically significant difference, but our confidence interval includes clinically meaningful differences. More data or studies are needed to obtain more precise estimates of our effect size. And then in the case where our confidence interval does not include clinically significant differences, we might say something like, our effect sizes most compatible with the data are not clinically relevant.
That's very helpful. So can you give us like the bottom sort of bottom line recap of what we need to know at the end of this conversation in terms of clinical and statistical significance.
So both inference, meaning, your standard hypothesis testing and p-value generation, and effect size estimation, along with confidence intervals, are critical for statistical inference and for the correct clinical interpretation of the results of our study. For further discussion of these points, you can refer to our shared urology guidelines titled Guidelines for Reporting of Statistics for Clinical Research in Urology. And I've highlighted guidelines 3.1 to 3.4, 4.4, 4.5, and our section on use and interpretation of p-values for reference.
Thank you so much, Melissa. That was so helpful. I'm sure our audience will learn a great deal. So thanks so much. And everyone, please make sure to check back in to get more installments of Biostatistics Chat so we can learn more about statistics and become a better writer and a better researcher.